Hi there. Welcome back to the formulaic approach. Today we are going to be discussing orbitals, all right, and basically quantum numbers and other principles that are associated. Okay, so you need this topic to be able to understand many other things in chemistry. So make sure that you sit tight and concentrate as you watch this video. Let your mind be here. It's going to be as detailed as possible in order for you to understand. So just stick with me. All right, now let's get into it. Now, what is an orbital? So, an orbital is basically, so let's start with orbitals. An orbital is basically any region in space, the region in space around the nucleus. Around the nucleus, where, and we're talking about a region in space around the nucleus, not just any region, okay? So the region around the region in space around the nucleus, where the probability of finding an electron is maximum or is high. Let's say high, okay? Typically the probability is greater than 90%. Greater than or equal to 90%. Okay? So basically, let's start with the word orbit. So when something, such as for example the Earth, moves in a circular path or moves around something, whether it's not, even if it's not circular, as far as it's moving around something, that path that it takes is called an orbit. So that already tells you that electrons, which is one of the fundamental particles of an atom, is revolving or going around the atom, right? So that region around that atom where we can find an electron that is already around it, that is moving around that nucleus, is going to be called the orbital. The region in space around an atom, around the nucleus of an atom rather, where the probability of finding an electron is greater than 90%, is greater than or equal to 90%, is called an orbital. Is that clear? So an orbital is basically, an orbital arises because of the wave nature of matter. So orbital arises because of the wave nature of matter, of electrons, wave nature of electrons, all right? And of course, they are, results of Schrodinger's equation. They are results of Schrodinger's equation. Okay, so basically, all of the orbitals that I might mention now, they are going to be equations primarily, okay, but we use those letters to represent them. So you need not know what is not compulsory, except you are doing advanced courses on it. It's not compulsory that you know those Schrodinger's equation, but first know what the orbitals are themselves, all right? But before we talk about that, let's talk about the key features of an orbital. The key features of an orbital include the fact that the maximum number of electrons that can enter an orbital, the maximum electron in an orbital is 2, okay? So the maximum number of electrons that you can see in an orbital is 2. But keep in mind, some orbitals are degenerate, okay? So when we say, for example, orbital P, for example, is degenerate. It's degenerate into 3 other orbitals, 3 suborbitals. So that suborbital is still talking about an orbital. So in which case we say that those suborbitals are still orbitals that contain 2, 2, 2. So it is degenerate into 3. So each of those 3 will contain 2, 2, which means that the p orbital is going to have 6 electrons. Is that clear? So I'm going to show you the orbitals that we have. Okay. Now, another thing about the orbital is that they are always filled. Electrons exist in opposite spin. Electron exists in opposite spins. So, for example, if I have an orbital like this, if I want to fill them, I always fill them in opposite spin, up and down. Is that clear? So it is, in respect of Pauli's exclusion principle. Okay, so that is why we actually do it this way. We fill them in opposite spin. Then, of course, all orbitals differ in their shape. All orbitals differ in their shape. Is that okay? Their shape, their orientation, their size, shape, orientation, size. Is that okay? They differ in those things. So these are the key features of an orbital. Now, what are the orbitals that we have? Or what are the orbitals we are going to be considering? The first one, now this way you should really pay attention. The first one is the s orbital. Now, the s orbital, the name s comes from sharp orbital. The s orbital exists in other orbitals, in all shells. Is that okay? So it's the sharp orbital, and it is the smallest because it contains its maximum number of electrons that can enter it. The maximum number of electrons is 2 electrons. Can contain what? Contains 2 electrons max. Is that okay? Then you will now say that, well, Master, you already said that the maximum number of electrons that can enter each orbital is 2. Why do I have to state that here again? Now, this is the reason. Other orbitals have degenerate orbitals. So when we say orbital, we might also be referring to suborbitals. Is that clear? So keep in mind that. Then the shape of this guy is spherical. So it is spherical in shape. So what's this spherical shape? Something like this. Is that okay? So that is the spherical orbital, and it is the closest to the nucleus. It is the closest to the nucleus. Closest to the nucleus. Closest. Okay, here. Closest to the nucleus. Okay, so that is that about the s orbital. It is spherical in shape, keep that in mind, and it is called the sharp orbital. Now, the second orbital you need to know is the p, and it is non-degenerate. S is non-degenerate. So the next orbital you have to know is the p orbital. Now, what does the p stand for? The p stands for principal orbital. It is the principal orbital. That's what the p stands for. Then it contains maximum of 6 electrons. It contains, okay, the first is that you should know that it is the first degenerate orbital. It is the first degenerate orbital. Okay? It is degenerate into 3 orbitals. Degenerate into 3 suborbitals. So, but of course, because we call them suborbitals, those spaces are still orbitals. They are still in the orbital, so we can still call them orbitals. But we use sub so that you know that they are inside the larger thing. Okay, so it is degenerate into 3. And if each of those 3 carry 2, then the maximum number of electrons that it can contain will be what? 6, contains 6 electrons maximally. Is that okay? So what are the degenerates of this? It is degenerate into 3 that we call the px orbital, p sub x orbital, the p sub y orbital, and the p sub z orbital. And this p sub z, these orbitals exist in perpendicular planes to each other. Exist in perpendicular 3D planes. 3D planes. And keep in mind that the orbital is also a 3D plane. It's also a 3D shape. So you can say any 3-dimensional region in space around the nucleus. Is that okay? All right. So, and the shape of this guy is dumbbell. Okay. Dumbbell shape. The shape of this guy is dumbbell shape, so it looks somewhat like this. I've showed you this time without number under our introduction to organic chemistry and all of that. So look at this. Now when you want to fill this, remember the same way we fill that is going to be according to a principle known as the Hund's rule, okay, of maximum multiplicity. Now you should go like this, singly first, before you now start pairing, provided you want to fill up everything here. Provided it to be filled up, exactly. So that's the p orbital. That's the p orbital. Okay, I wanted to mention something. The orbitals are represented by azimuthal quantum number. All orbitals are represented by azimuthal, the azimuthal quantum number, or the angular momentum quantum number. So, and there are four of those orbitals we want to consider: SPDFG. For those SPDF. So, for those of you that have seen the movie Power Rangers SPD, just use that to remember. Power Rangers SPD helps us to remember the SPDF orbital. So, this one has the azimuthal quantum number 0. This one is designated 1. This one designated 2. This one designated 3. Exactly. I'm going to treat this more soon. Is that okay? But I want you to just know that so that I've added the characteristics that it takes the azimuthal QN of 0. This one takes azimuthal quantum number 1. Exactly. So this guy takes the azimuthal quantum number 1. Now let's go to the next orbital, which is the SPD. So d orbital. Now what are the characteristics of the d orbital? Now just like we started with the name here, this one is called the diffuse orbital. The diffuse orbital. That's what the name is. The D stand for. Then it is also degenerate. It is also a degenerate orbital. Okay. Now this one is degenerate into something crazier. Now this one's, sorry, I said they exist in perpendicular three perpendicular planes. So if I wanted to draw that, I'll draw my y-axis that coincide. So they exist in perpendicular 3D planes, coinciding with the x, y, and z planes of our 3D Cartesian. So if we have y-axis, x-axis, and z-axis like this. Keep in mind that z-axis is going into and out of the board. So we'll have a dumbbell like this. This will be the piece of y. Another dumbbell that looks like this. This will be the piece of x. Okay? So they should actually meet at this point here. So piece of x will look something like this. Then the piece of z will look something like this. Okay? So this is PZ, PX, and PY. Alright, so this is what you have for the P axis, for the P orbital rather. Then this one is degenerate into 5 orbitals. So degenerate orbital is also a degenerate orbital into 5 suborbitals. Okay, so there are 5 suborbitals. Now what are the 5 suborbitals? We have the DXY, we have the DXZ, we have the DXZ or DYZ rather, YZ, then we have the DXZ, of course, we have the DXZ, then we have the DX squared minus Y squared, then we have the DZ, 1, 2, 3, 4, so we have the DZ squared. Is it clear? So these are the 5 degenerate orbitals. So if it's degenerate into 5 suborbitals, what will be the maximum number of electrons that can enter into it? So this one will take 2, this one will take 2, this one will take 2, this one will take 2. So if all of them take 2, then the maximum number of electrons that can enter is what? 10 electrons maximum. Is that clear? 10 electrons. So that proves, I'm going to show you something now. So that is this. Then the shape of that is, this one is dumbbell. So this one is double dumbbell, or what we call clover shape. Is that okay? Clover shape. Okay. And it is represented by the azimuthal quantum number 2. If this one is 1, this will be 2. Now, just focus, okay? Focus. Because if you don't understand some of these details I'm starting with now, when we begin to designate quantum numbers, you might not understand what I'm saying. So let's go back again. I said S is the sharp orbital, and it is it has the spherical shape, and it has maximum of 2 electrons. P, degenerate orbital, degenerates into Px, Py, and Pz, has maximum of 6 electrons because each of the 3 will contain 2 maximum. 2 has maximum number of electrons. And there is dumbbell shape. The dumbbell shapes exist in the at right angles, at the 3D right angles. Then has the azimuthal quantum number 1, S has the azimuthal quantum number 0. The d orbital is diffuse, degenerates into dxy, dxz, dyz, dx squared minus y squared, and dz squared. Then has the shape, clover shape, and azimuthal quantum number 2. Then the last orbital that we want to see is the F orbital. So it's the F orbital. So the F orbital is called the fused orbital. Fused orbital or fused orbital. This will be fused. The fused orbital, that's why it's called F orbital. The fused orbital, we now have the what? So we said that's the name. Then there's also degenerate. This one is degenerate into 7. Okay, degenerates into 7 orbitals, 7 suborbitals actually. Okay, so if you want to fill this, we didn't even mention. So this one, we'll have something like this: 1, 2, 3, 4. So that if you want to fill, we'll fill according to Hund's rule still. Singly first: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that clear? So, but this one, since it's degenerate into 7, we'll have this. 1, 2, 3, 4, 5, 6. So if we want to fill this, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Is that clear? So it means it is degenerate. That is, each of these must contain 2. Each of these orbital or suborbitals here must contain 2 electrons maximum. So if that's the case, then it can contain maximum of what? Of what? 14 electrons. Now the next thing you should also know about it is, now we've talked about, now the shape is a complex shape. It has a complex shape. The shape is complex that no particular name is designated for it, okay? And the azimuthal quantum number of this guy is 2. That one is 2, this one will be 3, sorry. So the azimuthal quantum number of this guy is 3. Now, one thing you should know is that the d orbital is the one that we see in transition metals, okay? The d orbital exists in transition metals. But F orbital, on your periodic table, we say the D block elements, they are the transition metals. Then of those, we have the F block represents the lanthanide and the actinides. The lanthanides and actinides. Okay? So basically that's what we have for the orbitals. So these are the 4 orbitals. Now let's go into the principles that we use to fill orbitals, the principles we use that guides everything concerning these guys, quantum number, filling of orbital, and all of those things. I like to start with the basic one, which is the Aufbau's principle. You have seen it before, you have seen it being used, but you probably don't know the name. So it's the Aufbau's principle. I mean, who wouldn't know this? SS1, okay? Aufbau's principle. I mean, if you don't know it, so just stick with me. Stick with me, it's very simple. Now, the word Aufbau actually comes from the German word. The word Aufbau comes from the German word. So it's a German word, okay? The Aufbau is a German word. And that German word Aufbau means building up. It's not a person's name, okay? It's not a person's name. It means building up. And the principle says that electrons enter into orbitals. Electrons enter into orbitals by building up from, so electrons are filled into orbital, or enter, let's use that, enter. Okay, let's use field, are filled into orbitals. So this is like, I'm stating the principle with reference to someone who wants to fill the orbitals, okay? Are filled into orbitals by building up from lower energy levels, to higher energy levels. So what that means is this, that an electron will not enter a higher energy level before the lower energy level. It has to go from lower to higher energy level. So that's what the Aufbau's principle states. Now in context, let me show you how we build it up. This is how we build it up. So this is how to do it. I'll tell you why when we start quantum number. So this one, you write 1 once, you write 2 twice, write 3, write that thrice, 4 times, quadruple, 5 times, up to 7 like that, okay? So I'm just going to stop here, 6, 6, 6, 6. But you should write them 6 times like that, and 7 and 8, and 7, 7, 7 like that. Now there is this why I stopped here, because for our first 20 elements, for our periodic table of elements, all of what I have here can suffice for what I need for those 180 elements. So we'll now start writing the orbitals, designating the orbitals here. So here we have S, here we have S and P, here we have SPD, here we have SPDF, here we have SPDF, if there were more, G, here SPDF as well, if there were more, GH, SP, blah, 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 like that. Now, you ask me that, now what do these energy levels correspond to? On your periodic table, how many periods do we have? Remember, we have 7 periods. So these are the 7 periods on your periodic table. So, or they correspond to K, L, M, N, O, P, Q shell. Is that okay? Remember, we have 7 shells also. So those 7 shells too, they are like this. Like this. Now, remember that we just said that S orbital can contain 2 electrons, P orbital, from what we wrote there, can contain what? 6 electrons. D orbital will be able to contain what? If you look at it well, they differ by 4, right? So it will contain 10. SPDF will contain 14 electrons. So they differ by 4. So what that means is this. In your K shell, you remember that, you know, the electronic configuration, we say that KL, shell, K contains 2, this one 8, this one 8, this one 2, 8. Actually, K contains 2. So if K contains 2, what does that tell you? That shows you that it has only S orbital. That's why it's containing only S orbital, no P orbital here. But L can contain 8 electrons. How did the 8 come about? S will contain 2 maximally. P will contain 6 maximally. So 2 plus 6, 8 that you are looking at here. So we have 8. This is also correct. But for M, now this one is to be useful for octet rule. Is that okay? That's why we use this. Actually, for M, from what you can see already, M is going to be 2 plus 6 plus 10. That's going to be 18. Yes, that's going to be 18 electrons that can actually enter M orbital, or the 3rd energy level. N, or the 4th energy level, can actually accommodate as much as 2, 6, that's 8, plus 10, 18. 18 plus 14, that will be 32. So N can accommodate as much as 32. And if you keep calculating like that, you get how much they can accommodate. I mean, of course, you tell me, I'm asking about G. G is going to have what? Maximum of 18 electrons. If we continue this, okay? SPDF, GHI. But then you ask me that, why did I not put it here? It is because for our 180 element, these 4 orbitals actually work, okay? These 4 orbitals are the ones we need. So that's why I'm not adding G. Now keep all this in mind because they will soon start making a lot of sense. So now I've discussed the Aufbau's principle. Now let's discuss the next principle that you have to know. That is, let's talk about we want to fill in an orbital now. So let's talk about the Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Now, this Hund's rule of maximum multiplicity is what we use to fill electrons. It states that electrons enter, it states that electrons enter into orbitals singly first. Electrons enter degenerate orbital. So the orbital has to be degenerate. Degenerate orbital. And I mean to say that this principle is only practicable with degenerate orbital. It doesn't mean that with non-degenerate orbital like S is the only non-degenerate. It doesn't mean that it's not practicable. But you can only visualize it you can only see it happen in degenerate orbital. Because of course, for S, if I wanted to fill S, I'll just draw this and draw up and down spin. Is that clear? But the principle of filling singly first holds with what? Degenerate orbital. So it says that electrons enter degenerate orbitals singly first before pairing. So electrons will pair, but before they pair in degenerate orbitals, they have to first what? Enter singly first. So they enter singly first with parallel spins before pairing. So that's the way we write it. They enter singly first with what? Parallel spins. Let me show you that. Parallel spins before pairing. Now let me show you what that means. Let's fill this p orbital now. I have my p orbital here. 1, 2. I want to fill in. Let's say I have 2p6 electron. So if I have this, I want to fill this. This will be px, of course. This will be py. This will be pz, or 2pz, 2py, 2px. Now, how do we fill this? We fill it singly first, like this. 1, 2, 3. You can see parallel spins first, right? Before we pair them up. Is it clear? So that is Hund's rule of maximum multiplicity. But the rule of maximum multiplicity itself, let me show you what it states here. The rule of maximum multiplicity itself is, this is how it works here. You know this one, the first rule, the first view or the first perspective of the Hund's rule is how to fill electrons in the degenerate orbital. The other perspective is how that when electrons actually enter into orbital like this, the way they are filled is dependent on the stability of the atom. Okay, I'm going to show you what that means. So one thing I forgot to do, I'm sorry here, is to show you how we actually build up orbitals. How do we build them up? We go like this, we follow this arrow like this. We follow this pattern like this. You see, I'm drawing a diagonal like this. In this direction, in this direction, in this direction. So we follow the direction of the arrow to write them. So for example, if I say write the electronic configuration of, now if you want me to show you another video on how to write the electronic configuration, let me know in the comment section. So we want to write the electronic configuration of magnesium, for example. Now magnesium is number 12, right? So it will look something like this. 12 electrons. I want to fill in 12 electrons. So it will look something like this. I'll write 1s first. So after 1s should be 2s. After 2s should be 2p before 3s. So this is the order of their energy levels, okay? This is the order of their energies. Then 3p before 4s. 3p before 4s. Now actually, we now have 3d before 4p and 4s. So what does this tell you? This tells you that 3d orbital has more energy than 4s in some cases. And in other cases, 4s we have more energy than 3d. Now in which case, 4s only has more energy, has greater energy, has more energy or greater energy than 3d for ionizing atoms. When an atom is ionizing, that's when 4s usually shows its power. But for a ground state, an atom in the ground state atom, an atom in ground state, then ground state atom, then the base electronic configuration is such that the 3d comes after as a higher energy level than 4s. Exactly. I'll show you that in perspective when I want to retrieve this maximum multiplicity. Now that's why I remember now. So let's fill in the 12 electrons in magnesium. How do we fill it in? Now, 2 we enter. The maximum that S can take is 2. So we put 2 here. The maximum that this S can take is also 2. How many will remain? We have filled 4 already. So remain 8. Here, 6 is the maximum that can enter here. So 6 has entered here. So 6 plus 2 plus this 10. So remain 2. So 2 will enter here. So it means that these remaining ones you are seeing here is useless. So for that magnesium, so magnesium electronic configuration is drawn this way. If you are told to draw the orbital diagram, the orbital diagram will look like this. So this one is the 1s2. How do you feel it? Feel the electron 1, 2 with opposite spins. I've mentioned that before. Then the 2s. Now when you want to draw the 2s, you must not draw it on the same line here because it's the higher energy level. So we'll bring it up here. So 2s2 will look like this to show that it is at the higher energy level. So this 2s is full 2, right? So we'll go again 1, 2. Then 2p. Now 2p can go just a little higher than s, but either way it's still 2 energy level, second energy level. So you can put them at the same line either way is 2. So this one 1, 2. How do we fill? We want to fill the entire 6. So singly first, following Hund's rule. 1, 2, 3, 4, 5, 6. Is it clear? So that's Hund's rule. Then the 3s, you see, the 3s orbital is going higher above all of this guy. So this is 2p6. So this is 3s2. How do we fill this in? We go 1 and 2. So this is the electronic configuration for magnesium, and this is the orbital diagram. Is it clear? So this is the orbital diagram. Now, one thing you should take note of is how I filled in these electrons. So because a question might come like this, that an electron is filled this way, an orbital is filled this way. 1, 2, 3, 4, 5, 6. Then they ask you, whose rule was violated? Now looking at this, the rule that was violated is there are 2 rules that are violated here. The first rule is Hund's rule. The first rule is what's it called now? Pauli's exclusion principle. Because it's Pauli's exclusion principle that helps us to know that these electrons have opposite spins. They have what? Opposite spins. So that is violated. But you also saw the way I filled it. I filled it like this: 1, 2, 3, 4. This is wrong. The way you feel it is, so this is singly first. So Hund's rule is violated. But it's not very obvious here that Hund's rule is violated. Let me show you how to make it obvious that Hund's rule is violated. How is Hund's rule violated? If you have something like this, once you see that you have double, this thing has paired up without entering this one, then Hund's rule has been violated. Should I repeat that? I said I want to see that the initial suborbitals have actually doubled and one of them is not paired yet. Then, or it hasn't been filled at all rather yet, then Hund's rule has been violated. Is it clear? Alright. So let's go further. Now we know how to fill this. If I say write the electron configuration of calcium, it will just be this, 1s2, 2s2, 2p6, 3s2, then we'll continue. After 3s, what will come next? We'll go down like this. Okay, 3s is 3p. We'll fill 3p6. So 6 plus that 12, 18. We need 2 more, then 4s2. That will be the calcium electronic configuration. Now let's go on. We have what's the next thing we have? Okay, the other rule. Okay, I said I wanted to show you the maximum multiplicity now. Now, this is where maximum multiplicity actually works. Maximum multiplicity. I said that for an atom in its ground state, the 3d orbital is at a higher energy than the 4s orbital. But for an ionizing orbital, an ionizing this guy, what's it called now? Where is it now? This 4s is going to have a higher energy than that guy. For example, let me show you how do we feel this guy. How do we feel iron? Let's feel iron, for example. Let's feel chromium. Chromium is number 24, iron is number 26. So let's feel both. Now look at this chromium, number 26. See how do we feel it? We are going to have 1s2, 2s2, then 2p next, 2p6, 3s2. I know I've not gotten there because I'm going to 24 electrons, right? 3s2, after 3s2, 3p6, so we have to be careful now to go. 4s2 again. How am I knowing the values on top? You know the maximum that each of these orbitals can take, right? This one is 2, this one is 2, this one is 6, this one is 2, this one is 6, this one is 2. Now if we count all the electrons that we have here, we have 2 plus this 10 here, 2 plus this 10, plus 2, 11, 12, 12 plus 6, 18. 18 plus 2 is what? 18 plus 2 is 20. Now we need 4. Now look here, we have 3D rather next. Now this 3D is 4 here, right? This 3D is supposed to be 4 here. This 3D is supposed to work 4 here. Now, this is the expected electronic configuration. This is what you should expect. But actually for chromium, it is not like that. For it to be in the stable state, for it to be more stable, for more stability, chromium prefers to have this electronic configuration. 2s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. Why? Because the 3d orbital, or the d orbital, generally, the d orbital is more stable when half filled. The d orbital is more stable when what? Half filled. So for you to have something like this, it will prefer to stay in this way because 3D will be more stable when it is half filled. Remember, it is 3D10 that fills it up, right? D10. So it will prefer this orientation, configuration. Is it clear? To prefer that configuration. Now, let's go to the next one. So let's go to the next rule. So we have seen Hund's rule of maximum multiplicity. Let's see Pauli's exclusion principle that I've been talking about. Now, Pauli's exclusion principle. Now, this principle states that no two electrons can have the same. No two electrons, or just let's say two electrons cannot have the same number set for all 4 quantum numbers. Now, how do we put this in context? We have to first learn of what? Of the 4 quantum numbers. Now, before we can learn of the 4 quantum number, another principle that why do we need the 4 quantum number first? So is where I want to state one more principle now, which is the Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. You remember that this principle is saying that, that's what I call it uncertainty, that is saying that there is an absolute limit to the accuracy of measuring the position, the exact position and momentum of a particle at a given period. So according to his principle, what he's saying is that it is impossible to measure the exact position and momentum of an electron simultaneously. So that's why I said there are many ways you can state the principle. You can say that it is impossible to get the exact position and momentum of a particle simultaneously, or there is an absolute limit to the accuracy of the position and the measurement of position and momentum of a particle with simultaneously at the same time. Exactly. So that's the uncertainty principle. So, but we can get as close as, so why did I state this principle? Is that we cannot know the exact location of this thing now, but we can get as close as possible to the electrons. And how do we find those electrons? We use the 4 quantum numbers. We use the 4 quantum numbers. So make sure you have written all this, because I'll be claiming them. Now we need the 4 quantum numbers to be able to bring us as close enough to an electron as possible. Okay, we want to find a particular electron. Let me show you what this works for. So I ask you to find me this electron. You know, inside this 2p6 electron, 2p6 orbital, we can find the 2p1 orbital electron. We can find the 2p2 electron. The 2p2 electron is different from the 2p1 electron. Electrons are distinct, okay? We have the 2p3 electron up to the 2p6 electron. So if I say find me the 2p3 electron, it's different from the 2p2 electron. That is, if I analyze, get the 4 quantum number for this 2p3 third electron, the 2p second electron will not have the same. That's what the Pauli's exclusion principle is saying, that the 2p second electron cannot have the same number for all the 4 quantum numbers for as the 2p3 electron. That is, the 2p3 electron and the 2p2 electron, 2p second, 2p first, and 2p third electrons, they will have at least, they will differ at least in one of their quantum numbers. They will differ in one of their quantum numbers, even though they exist in the same energy level, in the same orbital. Is that okay? So let's see how that comes out. Now, the first thing you have to, let's learn of the quantum number. The first quantum number you must know is the principal quantum number. The principal quantum number, and it is denoted by n, the principal quantum number n, small letter n. Now, this gives information about the energy level of a particle. The energy level of a particle. That's what this one gives information about. The energy level of a particle. And on that periodic table, since we have 7 periods, it means we have 7 energy levels. So those things you saw me write, KLMNOPQ, and 1, 2, 3, 4, 5, 6, 7, they are the 7 energy levels which the principal quantum number designates. So they can range from where? 1, 2, 3, 4, blah, 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 blah. Depending on, if we are, for example, we have 118 elements now. If we're able to have 1,000 elements, then it will continue, okay? It can continue. So it starts from, it takes integer values of positive 1, 2, 3, 4 and above. Never takes a negative value. This one, principal quantum number, never takes a negative value. So those numbers that I wrote down there now, it is this guy that helps us to know it, the principal quantum number. So for example, if I write an electron, 4p fifth electron. If I say, tell me the 4p fifth electron. Now, what is the principal quantum number of this guy? You simply say that n equal to 4. How did I know that? Because this is the 4th energy level, so n will be equal to what? 4. Is it clear? All right, follow me. Now, the next energy level you have to know is the, this one has plenty names. It has the azimuthal quantum number, or the subsidiary quantum number, or the angular momentum quantum number. But I like to call it the angular momentum quantum number. or the azimuthal quantum number. The azimuthal quantum number L, small letter L. All of these quantum numbers are, no, not all, or primarily, yeah, all of them are designated with small letter. So this is small letter L, okay? Small letter L. Now, the azimuthal quantum number tells us the sub energy level is called the orbital. So it gives information about what? Gives info about the orbital. So you notice I said those orbitals that we discussed the other time, we said this one has the azimuthal quantum number 2, right? How did we get that? It is actually that azimuthal quantum number gets its value from the principal quantum number. So for every n quantum number, comma, L is always going to be from 0 to n minus 1. L will take any of the values between 0 to n minus 1. So for example, if for that example I gave 4p fifth electron, for example, 4p fifth electron, and I have said that the n for this guy is 4 because it's in the fourth energy level. Now, which orbital can we find out fifth electron? Which orbital? It is the p. How did we get it? Let me show you. You know that we said that for any n, L will take values between 0 to n minus 1. So if our n is 4, L possible values will be 0, 1, 2, 3. We'll stop at 3. We'll now get to 4. Why? Because it is n minus 1. Is it clear? So that is 4. So that is n minus 1, which is 4 minus 1, and we have 3. Now, these are the possible values you can get. Now, what do these values represent? If you remember, I told you S is designated as azimuthal quantum number 0, L is designated as azimuthal quantum number L, quantum number 1, 2 is the d orbital, P rather, S, P is designated 1, D is designated 2, and F is designated 3. Exactly. So, the d orbital is designated 2. So, that's how I knew that this is 2. In that place. Is that clear? Now, in this case, which orbital are you seeing here? The orbital you are seeing is P, right? So it means that the azimuthal quantum number for this electron we are looking for is going to be what? 1, because it's P orbital. So it's got to 1. So remember, the n quantum number is what will tell you the particular, will tell you the range of value for the L quantum number of the electron we are looking for. Now, which other quantum number helps us to find an electron? Is the magnetic quantum number. The magnetic quantum number M sub L. So there's M sub L, and there's the third one, which is called, the fourth one, which is called magnetic spin, or simply we say spin. Exactly, is that what we call magnetic spin quantum number, or the spin quantum number. Now, what does this one tell us? Now, this one tells us the number of degenerates, or number of suborbitals. Is that clear? Number of suborbitals that we can find. Is that okay? Now, the value of this one ranges from M sub L values, ranges from any negative L value we get, down to 0, down to positive L value. I said the M sub L values is also a range of values. Is that okay? It's also a range of values. This one is very simple. So if we get a particular L value to range from minus of that value to plus of that value. In this case, we got L to be 1, right? So in this case, we'll have we'll go from minus 1 to 0 to plus 1. If we had gotten 2, we'll go from minus 2, minus 1, 0, 1, and 2. If we had gotten 3, we'll go from minus 3, minus 2, minus 1, 0, 1, 2, and 3. Now let me show you one very nice, one very interesting thing. How many did we say p orbital was degenerating to? We said it's degenerating to 3, right? So this minus 1 here represents the p sub x. The first degenerate. This one represents what? Piece of y and piece of z. So that's why we have three entities here, because we have three degenerates in p orbital. Is it now making sense? Then this one also degenerates into 5. So we have 1, 2, 3, 4, 5. The dx, y, dx, z, blah, blah, blah that you are seeing there. These are the numbers that they represent. Is it clear now? Then f orbital 2 is also degenerate into 7. 1, 2, 3, 4, 5, 6, 7. So for example, if I was looking for 4f 12, for example, I'm looking for 4f12. What will I do? I'll just go to this guy. See the way I drew it? Then I'll separate it like this to show you all the degenerates, to separate the degenerates. Okay? The different suborbitals rather. Now, how do I fill? I have to fill this 12 because I'm going to the 12th electron. So I'll go 1, 2, remember, Hund's rule, singly first before pairing. 2, 3, 4, 5, 6, 7, all parallel spins. 7, 8, 9, 10, 11, 12. So this is the 12th electron. This is the guy I'm looking for. So I stop there. So the M sub L for that guy, the M sub L for this guy I just did now, where did he stop? He stopped at 1. So that would be what? 1. Is it clear? I hope it is clear. Now let's go to the next one, which is the magnetic spin. Now let's talk about the magnetic spin quantum number, or simply we just call it magnetic spin. Now M sub S, that's what we should denote it. Now this one tells us the orientation of the guy. It tells us what? The orientation of the electron. Orientation of the electron. So whether the electron is spinning upward, there are two orientations. Either upward spin or what? Downward spin. Okay? Upward spin will look like this. Downward spin will look like this. Is it clear? Now when an electron spins upward, it is designated spin quantum number. Because it is number, it is designated plus half. If it spins down, it is designated minus half. Is it clear? Upward spin plus half. Now downward spin minus half. Is this clear? So these are the 4 quantum numbers. Let's now go into the classwork. Now watch. It's very simple. Just follow me. Follow me. We are going to do this. Find me the following electrons. I say number 1, the 2p third electron. Number 2, the 1s2 electron. Number 3, the 3d7 electron. Number 4, 4f, let's use 11 electron, or maybe 4f9 electron. Then 5, the 5d3 electron, or 5d8 electron. Okay? So now let's solve this classwork. For the first one, we have the 2p3 electron. Now, we need 4 quantum numbers to describe this guy, to describe the location of this guy, right? So how do we get it? Now, what's the first quantum number we need? The principal quantum number. What does it tell us? It tells us the energy level, right? So simply look at this thing. Which energy level is this? Energy level 2. Right? Second energy level, so N is 2. Very simple. Now, when we get our N, our L is going to range from 0 to N minus 1. So this minus 1 is 1. Is it clear? Oh, good. Oh, no, we're in Nigeria. Hey, let's go, please. I hope you can still see this. Oh, go help us. So, turn the formula. So, like I was saying, L is going to range from 0 and it's going to be between 0 and 1 because it must be from 0 to N minus 1. So, and what does 0 stand for? Remember, what does the L tell us? It tells us the orbital. Which orbital takes 0? S. Which orbital takes 1? P. Now look at what you have here. What do you have here? You have P, right? So it means that the L for this guy is actually 1. Is it clear? So we've gotten the M quantum number and the L quantum number, the azimuthal quantum number. Now let's go to the M sub L. Now remember that for M sub L, it's going to be minus L to plus L. Now what is this guy? 1. So it's going to be from minus 1, 0, and 1. So this corresponds to the Px, Py. So I'm separating them like this. So it corresponds to Px, Py, and Pz. Actually, we don't need this. I just wanted to show you that. Now, how do we get this? So we'll fill it. We know we are going to 3, right? So we'll go 1, 2, 3. Who's that? So 3. So that's 3. So where did the 3 stop? This 3 here is on 1. So the M sub L for this guy will be what? 1. Are you following now? Now let's go. The M sub S. How will it look? The M sub S will show you the spin, right? Is this thing spinning up or spinning down? It's spinning up. So M sub S will be what? Plus half. So that is the answer. So the answers for number 1 are N equals 2, L equals 1, M sub L equals 1, M sub S equals plus half. Is it clear? Let's go to the next one. Let's go to the next one. Follow me. Follow me. The next guy, number 2. Number 2 is 1s2. We want to find the 1s second electron. What is M going to be? The energy level is in energy level 1, so we'll put 1. Is it clear? Then the next one, L will be between 0 to minus this, right? To this minus 1. 1 minus 1 is what? 0. So it's only 0 that we have here. So which orbital is 0? S, right? So L is going to what? 0. Now you can already see that S is what we have here. So 0. Is it clear? So what will be the M sub L? M sub L will be between minus L to plus L. This is 0. 0 does not have positive or negative, right? So already we know that M sub L is also going to be what? 0. That's why S is non-degenerate. Is it clear? S is non-degenerate. So, but of course, it is the 1s2. So M sub S will matter. Now we have, let's fill it. We have 1, 2. So we're going to go 1, 2. So this is the second one. It is spinning where? Down, right? So M sub S becomes what? Minus half. Is that clear? So this is what I'll do. I'll solve number 3. You will now solve number 4 and number 5. And you post it in the comment section. Or you send it to my WhatsApp number 09021416307. Or just add +23490 blah 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 like that. So now let's do the last one, 3D. I'm stopping because of the power that has been withdrawn. So we have N for this guy will be what? Third energy level, right? This is number 3. Third energy level. So N will be 3. L will be between 0, 1, and 2. We stop at 1 before that number, right? So what will be M sub L? Oh, first, sorry. So what do these numbers correspond to? S, P, and D. What do you see here? D, right? So our L definitely is what? 2. Because it's D we are seeing here. Now, if our L is 2, our M sub L values will be between minus 2, 0, 1, and 2. Minus 2, minus 1, 0, 1, and 2, like this. So we'll now try to, let's draw it into the orbital. Let's draw the orbital diagram rather. So we are filling 7, right? So we are going 1, 2, 3, 4, 5 parallel spins first, then 6 and 7. So this is the electron we are looking for. Now, where did this stop? It stopped at minus L, right? So the M sub L for that electron will be minus 1. It stopped at minus 1 rather. So it will be minus 1. So what will be the M sub S for that electron? Is it spinning up or down? It is spinning down. So that will be minus half. So that will be it for this video. Do have to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. And drop the answers for this one in the comment section. Or send it to this number, +234-9021416307. And if you need me to release any other video in chemistry, just let me know. Put the topic down in the comment section. I'm going to address it. God bless you.